We'd like to start the afternoon session of today's forum. The afternoon session's title is Hydrate Research Today. This is Professor Mori of Keio University.
Thank you very much for the kind introduction. During lunch, we found out that the wind is stronger and there's heavier rain, but thank you very much for coming for the afternoon session. Despite the severe weather, hopefully we'll have an active discussion here despite this situation. So, in the afternoon, we will be talking about specific studies and technologies. First of all, from State Institute of Molecular Sciences, National Research Council Canada, we have Dr. John Ripmeester. He's going to talk about changing concepts in craft rate hydrate.
Well, thank you for that kind introduction, Professor Mori. I'm greatly honored to be here, and I'd like to thank the faculty and staff of Keio University and the personnel of the Canadian Embassy for organizing this Hydrate Symposium. I think it's an excellent time to look at gas hydrates in all its details and its practical application as well as its fundamentals. I think the time is right for taking this whole field forward. My own interest in hydrates, of course, comes from the molecular scale point of view, and for a number of years already, there's a number of concepts in the class rate science world that are changing. I'd first of all like to acknowledge a lot of the people that I work with and the people that have formed a particularly strong hydrate team, and that especially my colleagues at NRC and a number of visitors that have come by and since gone back to their home countries, and also strong collaborations with Professor Inglesos and his group, and of course he is here, and also recently we have started to collaborate with Professor Omura. And I think that the hydrate world is very complex, and collaboration is the answer to dealing with this complexity. So here's my outline. I will give you I've got to keep my finger off the right button here. So I'll give you a brief introduction to structure, guests, the gas capacity of hydrates, and the fact that they are tunable materials. Then I will talk about the different scale on which hydrate research is done, and that each scale has its own methods. Then I'd like to get on to the theoretical description. The van der Waals and Plateau model dates back to the 50s, and look at some of the assumptions of the model and how it is used to do hydrate prediction today. Then I'd like to speak about the inadequacies of the model, which various experiments and molecular dynamic simulations have shown recently. And this involves guest-host interactions. Also, it's often assumed that the molecules and the cages are spheres, and we all know that this is not so. And also the concept that the guests are actually gas-like species, which also isn't exactly true. So just to show you the structures again, and many of you have seen these, so I will not spend much time with, but here we have structure 1 hydrate, its crystallographic description, the unit cell parameters, and the 2 cages that make up the structure. And of course, the 512 refers to the fact that there are 12 pentagonal faces, and over, in this case, 12 pentagonal and 2 hexagonal faces. And these pack together to give a nice space-filling structure. And of course, the oxygen atoms are at the vertices, and the hydrogen bonds are between oxygens. And then we have the cavities or cages which can hold the guest molecules. Structure 2, also cubic. different cage. This one has 4 hexagonal faces. This one looks much the same as in structure 1. And again, the packing of the cages together to give a 3-dimensional structure. And finally, we have structure H. There are other structures as well, but these 3 structures actually have been found in nature and have been the subject of much laboratory work. And here we have an unusually large cage and another small cage with square faces. So we can see that the water molecules inside the cage, inside the hydrate, can have all kinds of different geometries. We have square, pentagonal, and hexagonal faces. Okay, so now here we're looking at guest molecules, and what I've shown you is a plot of the largest van der Waals guest diameter given here, and then a list of molecules, and I've picked the rare gas molecules, also hydrocarbons, and some others such as CO2 and H2S, to show you a scheme that generally is followed as the size of a guest molecule changes and how the structure changes with that. I also show you here the hydration number, 5 2/3 for these small structure 2 formers, 5 3/4 for the small structure 1 formers, and then this changes to 6 2/3 as the smaller cages become empty, and we change back to structure 2. Here the small cages are empty and the hydration number becomes 17. For larger molecules, they do not form hydrates unless they have a help gas molecule with them. And this works in such a way that if we take some of these molecules and put in group some from 1A or from the ones up here, we form structure 2 hydrate again. And if we take these molecules with small molecules from group 1A or these, we get structure 2, although by themselves they do not form hydrate. And over here we have a large group of molecules that form structure H, as long as they have small guests with them either from here or from here. And there's one additional complication, and that is if we have small molecules from group 1A, so these by themselves form structure 1, and these by themselves form structure 1, but together they sometimes form structure 2. So it's a complex relationship, although I think this reasonably well shows how the system actually works. And the largest guest in a single hydrate usually determines the structure type. So now to look at the species that actually form hydrate, and in the first column are the molecules that we perhaps used to. We have the rare gases as atoms, and then more complex molecules and triatomics, hydrocarbons, and these others. And they all qualify as guests that are either insoluble or limited solubility in water. And it's often said that guest molecules have to be hydrophobic, but this clearly isn't true, because we do have a list of guests here which are water solubles, and they quite happily form hydrates as well. And there's clearly not hydrophobic molecules. And to become even less classical, we have a number of acids that form hydrates as well as some bases. So a guest can be any species that fit into the hydrate cages and that doesn't actually overly disrupt the hydrate lattice. And clathrate structures are robust enough that they can tolerate a wide variety of guest chemistry. So the field in that sense is much broader than just natural gas hydrates. One of the main ideas of clathrate hydrates is gas storage, and I thought I'd show you an example of that by looking at the methane capacity of hydrates. And here I've listed the structures, structure 1, 2, and 3, their designation in terms of small and large cages, and the number of water molecules per cage for structure 1, 2, and H, and the unit cell parameters. So the second column, I show you the methane content, the volume of gas at SDP versus the volume of the hydrate. And this is if all cages are filled with one gas molecule. And as you can see, surprising in a way, that all of these hydrates have exactly the same capacity for gas, except that the only one that is realistic here is structure 1, where all the cages, in fact, we can put methane into. For structure 2 and structure H, the large cage usually takes a different molecule, except at very high pressures, and then you can put methane into all the cages. So these are just hypothetical figures to show the comparison. On the other hand, we can put a large guest in the large cage and a small guest in the small cages, and then the capacities look like this. Except it's not very realistic that we can make a hydrate where there's a clean division of methane in small and large cages, so this is again a hypothetical situation. But for these two hydrates, it is realistic that we can fill all the small cages with methane and something else in the larger cages, and then these become the capacities. In the final column, I have some experimental numbers, and then we must, of course, add the temperature and pressure under which these measurements were made. And you can see that in this case, we actually come reasonably close to the maximum capacity. Whereas in this case, only about half the cages are filled under these conditions for a double hydrate in question here. And for this, we're actually a little bit closer to the maximum. But you can see that we have considerable leeway in designing a system for gas hydrates with specific purposes. The other thing that I wanted to mention is that one can tune the composition of a class rate hydrate. And the example I've picked here is that of THF, a THF hydrate with methane present as well. And these experiments were carried out under a constant pressure of 2 megapascals of methane. What we were changing here is the concentration of THF. And you can see that if you're working in this region, you have no methane molecules in the large cage, even though they will occupy the small cage. But as you drop the concentration of THF, you in fact start seeing methane in the small cage as well. And in fact, you can work yourself up to quite a large occupancy of the large cage with methane too. And of course, at constant pressure, this comes at a penalty of having to work at lower and lower temperatures. And we can, the experiment is in good agreement with predictions from the theoretical considerations, as long as you work in solution. If you try to do the solid state experiment, we seem to get compounds that are not at thermal equilibrium, and these will continue to change with time until they also become the equilibrium situation. But it is, again, a useful feature of class rate hydrates that by adjusting the fugacity and activity of the guests, you can fill cages with one or the other species in many different ways. I was going to talk just a little bit about scale of hydrate research, and of course where I tend to work is over here, the molecular and nanoscale, the world of molecules, and these are the length scales we're working with, and the times can be as short as picoseconds. The change between, say, the molecular nanoscale and the macroscopic, I've taken here fairly arbitrarily as on the scale of 1 micron, where we're now dealing with hydrate particles, sediment particles, and pore sizes and times longer than a millisecond. And finally, we have the world of geological strata and reservoirs, where times can be now up to years, and we're dealing with meters to hundreds of meters in terms of the volume of some of the reservoirs. So the thing that the two approaches to research that have happened here is, of course, is that problem solving obviously involves the real world and mainly macroscopic ideas. And if we want to know about structure or mechanisms, we have to enter the world of the molecular and nanoscale. And often, though, we run into difficulties or questions with our problem solving on the macro scale, and then we must take recourse to actually going over here to help and try to figure out what some of the problems are. And then the hope is that this will feed back into the problem solving area and improve our understanding at this level as well. And I think that we can all agree that the macroscopic models ultimately do need to be consistent with molecular and nanoscale concepts. A lot of people sort of start at this point and only look at this, but I think in many cases you come away with ideas that are scientifically unsupportable. Each realm has its own methods in terms of how theory is actually applied, and on the macroscopic side we have thermodynamics and fluid flow and mass transfer. We tend to work with a few variables in thermodynamics. Mechanical and non-mechanical variables are used, such as free energy and entropy. The system will obey the laws of thermodynamics. There's really no reference to molecular structure, and the lengths tend to be on the large side and the times on the long side too. Whereas on the molecular side, we deal with molecular dynamics. And in this case, we have many variables, as many as there are atoms in the system, so often Avogadro's number, and the variables are the velocities and the positions of the atoms. We only have mechanical variables, and the system obeys the laws of mechanics, either classical or quantum, and it is indeed based on molecular properties, and we deal with nanometer length and pico to nanoseconds. Of course, if these systems didn't interact in any way, it would be pretty useless. But the language of statistical mechanics allow us to connect the two and derive thermodynamic parameters from molecular dynamics, for instance. But, and of course, it has been interesting from the point of view of class rate hydrates that this connection was established many, many years ago. The statistical thermodynamics model, as proposed by van der Waals and Plateau, actually dates to 1959. And this is the basic equation that is used to describe class rate hydrates. And it takes free energy terms, like the mu values here. So this is macroscopic, and it relates it directly to the occupancies of the cages. And all the parameters are explained here. So this connects the microscopic world to the macroscopic world. And since class rate formation or hydrate formation follows Langmuir adsorption, the cage occupancies can in fact be written as in terms of the Langmuir constant and the partial pressure in the system. And of course, Langmuir constants can be calculated. And this is the form of the calculation that van der Waals and Plateau used. And once one has these different variables, we can do a number of things. We can, right from fundamental principles, calculate the using a Guest-Hose potential, calculate the Langmuir constant, calculate cage occupancies, and derive a delta U value. And of course, this is interesting since this value to a first approximation is the same for all the hydrates of the same structure. We can also do another thing, and that is if we have the occupancy ratio of the guests, so this would be an experimental number, and the composition, we can derive a free energy value experimentally. And of course, one can compare these two and see how well one is doing in terms of parameters. And thirdly, one can use the free energy and a cage occupancy ratio and derive a composition. So we can have an experimental method of determining hydration number. And this actually is surprisingly difficult to do it by standard laboratory methods. Here we have an instrumental method of doing it. And if you don't do it this way, then you have to have very, very pure hydrate samples, which is really quite difficult. So the original van der Waals and Plateau model has a number of assumptions, and they assume that the cages are spherical, the guests are spherical, and that the guest host potential depends only on the position of the guest in the cage, so it doesn't depend on the orientation of the guest. And the guests interact with the host via short-range interactions only, such as modeled by Leonard Jones' Devonshire potential. And the cage filling is not dependent on what happens in surrounding cages, or whether there are guests present or not. And the free energy difference between the hypothetical empty hydrate lattice and the water ice is constant for the same class rate structure type. And then what one can do is calculate compositions, dissociation pressures, enthalpies of formation. So one can use the van der Waals model to predict hydrate formation conditions and a number of different hydrate properties. And as van der Waals already pointed out, this model works for rare gas atoms reasonably well for spherical guests, as long as these are not soluble in water. So the current prediction models actually haven't really changed from the van der Waals model, but they've been parameterized in a number of different ways. And in this particular case, this is an adapted form of the van der Waals equation, and these terms only are correction terms for operating away from standard pressure and temperature, but the rest is much the same as I showed you before. Today, the guest-host interactions are derived from a Kihara potential with spherical or linear core, guest species with dimension derived from a variety of sources, including virial coefficients, but they're still assumed to be spherical species. An interesting difference is that a term in A, W, has been added, which is an activity correction for water-soluble guests. But you can see, even though on the macroscopic side we've corrected for this, on the microscopic side, nothing has been put in for this water solubility. It still reflects only short-range interactions. So we've now established an imbalance in this equation. So all the guests are in fact treated essentially as variations of noble gas atoms. And I think this is not a good assumption anymore. So the parameterized versions of this model are then used to predict hydrate properties. And the parameters are optimized by fitting to experimental data to improve performance. But what is lost, in fact, is the fact that there is real chemistry going on in the guest-host interactions. And they basically have disappeared from the considerations here. And you can see from this table that chemistry is important, because what I'm showing you here is groups of 3 molecules that are quite similar. The top one in each set of 3 is a hydrocarbon. The second one, we've replaced a methylene group with an oxygen or a sulfur, an oxygen here and then a sulfur, or we've replaced a methyl group with an OH or an SH. And basically what this does is that these molecules are all structurally related, and in size they're not that different. But you can see that the center row in each of these cases, the stability field of the gas is far less than that of its neighbors. And what this says is that all these gases that contain oxygen are different from the other ones. And this is clearly recognizable if you look at a table like this. So obviously, chemistry is important. And It's been many years since a chart like this was known, but people have concentrated on dealing with the hydrocarbons, of course, and not worried too much how their models worked for other guests. So to look for these guest-host interactions, which must exist in these oxygen-containing molecules, the old measurements where this became apparent that the hydrates had fast water reorientation times, and this was measured on a time scale of microseconds. More recently, we can use MD simulation, and what we do there is look for the short guest water distances, shorter than one would expect, and also misdirected water OHs. So we're looking for guest-host hydrogen bonding. And this is done on a time scale of pico to nanoseconds. And then single crystal X-ray diffraction. Here, of course, we can actually determine the relative positions of the atoms, both of the guest and the host, and look for guest-host interactions with distances less than the sum of the van der Waals radii. And if you find these, this means that there is a special interaction that a short-range model just would not have. The two molecules that I will show some results for are pinacolone, which is this one over here. So it's a ketone, and this one over here, tertiary-butylamine. And both of these are capable of hydrogen bonding, the ketone through the oxygen, and the butylamine through the nitrogen. So this represents pinacolone in the structure 1 large cage, and the two pictures are consecutive snapshots from a molecular dynamics simulation. And the simulation was done at 250 Kelvin. So on the left side here, you can see there's the guest molecule and there's the host water. And the guest molecule is just floating around inside the cage. It's not really close to anything. But in this particular, the next snapshot, you can see that there now is a short guest-host interaction. So at certain times, this guest molecule does form a hydrogen bond. And you must remember, this is not a real experiment, this is a simulation. This shows a simulation now for tertiary-butylamine in the structure 2 large cage. And you can see that here we have a hydrogen bond, and at a certain time later, the molecule has moved a long ways, but it again forms a hydrogen bond. So here we have a situation where the guest seems to be always hydrogen bonded to the host lattice, and then it can move and that forms a new hydrogen bond. So it's always hydrogen bonded, but it hydrogen bonds in different places. And what really makes excellent proof of all this, that what we're seeing with the molecular dynamics simulation, is that we can also see this with X-ray crystallography, where we can actually locate the atoms of the guest and the host. So here we have the pinacolone in the structure H cage, and you can see we do find a short distance between the ketone oxygen and one of the water molecules. And we can assume that there is a hydrogen bond here, which is relatively weak. On the other hand, the other case we worked with, where the guest was hydrogen bonded all the time, you can see that there is in fact a strong hydrogen bond over here, and then in fact the water molecule to which it is hydrogen bonded has moved out of the normal position of the cage by 1 angstrom. So we have a distorted cage. And you can see that this now breaks one of the assumptions of the van der Waals model, that by distorting this cage, it also has an effect on the neighboring cage. So cage filling is now going to be connected. So now I'm going to talk a little bit about other ways of looking at how guest symmetry is important in determining the properties and some of the spectroscopic measurements that we have done on hydrates. And the two methods that we've been using is single crystal X-ray diffraction, where we can locate and localize the guests, but we can also do this with NMR spectroscopy. I don't have time, of course, to introduce you to NMR spectroscopy in detail, but in the solid state, the spectrum of a spin-1/2 nucleus looks like this, and for a spin-1 nucleus, it looks like that. And these are for guest molecules that are static, that they're not rotating, they're just statically held in a lattice. If you then put these into cages of different shapes, if we put these in a spherical cage, we get isotropic motion, and we get complete averaging of these anisotropic interactions, and we end up with a sharp line. On the other hand, if we have a non-spherical cage, we get anisotropic motion, and we get different variations of asymmetric lines, or we get some residual doublet splitting. So the conclusion is that just by looking at the guest molecules in a cage, we can tell what the cage symmetry is, which is a very useful thing, especially if you cannot grow a single crystal to do crystallography. So I've shown you here the results for a structure 1 CO2 hydrate, and this is in the large cage, and I've lost the radius here, but the variation in the large cage radius is about 14%. Now in the models that people use, this cage is assumed to be spherical, but then you can wonder how important is this 14% asymmetry. Well, if you use X-rays, we can look at the large cage from two directions, and you can see that the guest molecules here look like they're distributed in a circle, and if you look at them from the side, you can see that they're more or less located in the plane of the cage. And you can see now that this cage really doesn't look very spherical, and the guest molecule knows it. It stays near the plane. In the small cage, which on the other hand is more or less spherical, you can see that from any direction, the distribution of the guest would look like this. So to assume a spherical cage for the small cage in structure 1 is fine, but for the large cage it is not. Now from the NMR point of view, we of course do not locate atoms and molecules, but we can assume that our cage is flattened like this, and that our guest molecule is going to lie somewhere in between. Well, we can assume that it might stand up here, or it might be in this plane, or somewhere in between. And if we look at the spectrum here, we can see there are two components. There's this sharp component, and this then reflects the guest molecules in the small cage, which are spherically distributed, and it is an isotropic line. And you can see that for the other guests, we have an anisotropic pattern. That means that the guest molecule is somehow localized in the cage. It doesn't have a spherical distribution. And we, of course, can quantitate this with an order parameter. And the order parameter here we've used is 1/2 3 cos squared theta minus 1, where theta is the angle between the axis of a linear molecule and the plane of the cage. If the guest is not moving, the order parameter is 1. If the guest is rotating in the plane, the order parameter is 0.5. And if the guest is rotating isotropically, the order parameter is 0. And for a number of linear or pseudo-linear molecules of different length, we've actually measured these patterns by NMR and derived these order parameters. And you can see that for carbonyl sulfide, the order parameter is very close to 0.5, so it's almost located completely in the plane. For the smallest molecule, methyl fluoride, which is hardly a linear molecule, but we can still approximate it that way, the order parameter is 0.11, which means that the guest is getting much closer to isotropic rotation. And of course for methane, which is not a linear molecule at all, the order parameter is 0, and the molecule does indeed rotate isotropically. So you can see that the volume that is accessible to the guest, in fact, is determined as much by the guest as by the actual cage geometry, because the cages are pretty much the same for all of these, but it's both the guest deviation from spherical symmetry and the shape and size of the guest inside that determine where it actually sits in this cage. But you can certainly see that it does not behave like a spherical cage towards these guests. Just to show you that we've made considerable progress in being able to do NMR on different species. When I started my work many years ago, all the work was done with protons, spin a half, which means it's an easy nucleus to use. The natural abundance is very high, and the receptivity is also very high, it's nearly 6,000. And this is compared with carbon-13, spin a half, but natural abundance is only 1%. And this was fairly arbitrarily assigned a receptivity of 1. But you can see suddenly, to do NMR on carbon-13, we had to overcome this difference of a factor of nearly 6,000. And this was done quite successfully. Carbon-13 is now a fairly routine tool for using in NMR spectroscopy. But just recently, we've been able to use NMR to look at sulfur-33. It's a quadrupolar nucleus, which means it's difficult. The natural abundance is even less than that, and the receptivity is another factor of 20 or so less, 50 or so less than for carbon. To be able to do that, you need a pretty heavy-duty NMR instrument. So you can see this is a 900 megahertz instrument, which we use to do the sulfur-33 NMR. It's a huge magnet. If you've seen NMR spectrometers, this is probably one of the largest you're likely to see. Here's a spectrum now for SO2, structure 1 hydrate, and you can see that there are two contributions, one from SO2 in the large asymmetric cage and SO2 in the spherical small cage. And also here we have H2S in the large cage and H2S in the small cage. So we can now look at these structures and measure the cage occupancies and the distribution of guests among the different sites. It's just a summary of don't worry about all the numbers, but what I'm showing you here is the cages, all the cages that we have come across in the three structures, their symmetries, their approximate sizes, and then a bunch of NMR parameters. To make it easier to follow, there are two spherical cages amongst these, the ones with the red arrows here, and you can see what you would see for this is just a sharp single line, no features, just a sharp line. And that means that we only have a chemical shift to look at. There's no anisotropy parameter, these are 0. If we now go to cages with axial symmetry, we have these three. The kind of pattern that we might expect for that is this. And here we have a chemical shift, but also I should be working with this actually for carbon. We also have an anisotropy. So here we have two parameters. For that one we have 1, for this we have 2. And we have one cage that is completely asymmetric. That is this one here. And it gives a pattern that looks like that. So we have 3 features. There's a shoulder, a peak, and another one. So there we have 3 different parameters, and this just shows you that it's relatively straightforward to use NMR to determine the symmetry of the cages in which the guests actually reside. Just a final look at some dynamic properties of spherical guest molecules in hydrate cages. And this pertains to the fact whether guest molecules can be thought of as gases. And over the years, we've been able to measure a number of rotational activation energies for rotation of the guest in the cage, and we've been able to do a number of these spherical molecules. You can see that for all of them, in fact, there are barriers to rotation, even though they're quite low. And at room temperature, RT is equal to this, and you can see that, in fact, the barrier to rotation is less than the energy at room temperature. So you might almost start to think of methane as a gas phase rotor in the hydrate cage, but it still has a low energy barrier, as do all these other symmetrical molecules. So the three situations that we've come across then, and I've mentioned some already, if we have non-spherical guests and non-spherical cages, they behave as spatially confined, so they're anisotropic and they're hindered rotors. These have tensors, and a tensor property is characteristic of the solid state. So they're not gases at all, they behave much like solids. Spherical guests and non-spherical cages behave as isotropic hindered rotors, and those were the blue ones that I've shown you here. And guests in spherical cages behave as isotropic rotors as well, and those are those, but they all do have barriers. So, summary, in general, guest-host interactions are much more complex than those described by Leonard-Jones or Kihara potentials. And the long-range interactions, such as hydrogen bonding, must be included in order to understand class rate chemistry. Some cages are actually quite non-spherical, and for non-spherical guests and non-spherical cages, the interactions are quite anisotropic, and it's generally a bad approximation to assume otherwise. And in terms of gas molecules, cannot really be described as gas-like, as the gas dynamics are governed by the symmetry of the cage, which is definitely a solid state features, even though some guests have low rotational barriers and are getting close to be free rotors at 273. Finally, some suggestions for improvements. That in calculations of hydrate stability and composition, we should use guest-host potentials that capture all significant guest-host interactions, not just the short range, but also the long range ones that, that describe hydrogen bonding. The true dimensions of cages should be used rather than an average spherical equivalent, and molecular dimensions of the guest rather than average spherical equivalents for the molecules as well. And I think only this way we can develop new knowledge and insight into class rate hydrates. And we have to at least acknowledge that we should be utilizing molecular scale concepts, or at least making sure that our models are consistent with molecular scales. And finally, I'd like to thank you for your attention.
Thank you very much indeed. Some molecular level consideration of hydrate, how far we have come in terms of understanding. And it seems that we have gone a bit longer than scheduled, but if there are questions, we would like to accept one or two. Does anyone have a question? No? Okay. So maybe during the break later on, I will have an opportunity to ask questions directly. Thank you very much.